Hello, hello. All right, so this is our 2.3 lecture video over the composition of functions, okay? So what we're going to be talking about is how to compose functions, which is very different from the algebra of functions. And then we're going to go into specifically how this affects the domain of these functions, okay? And then also how to evaluate functions that have been composed. All right, so first of all, let's just go straight into what composing functions is. So composing functions basically means we're taking one function and plugging it inside the other function as its input. So no longer are we doing like this one plus this one, or this one minus this one, or this one times this one. We're actually putting one inside the other function, okay? So if we have something, some of you may have learned this as fog, right? F of G is how we say this, okay? So if F is composed of G, whichever little function here is closest to our input, that's the function that's going to go in the inside. Or you can think of this as X goes into G and then G goes into F. Okay, so whichever one's closest to our input, that's going to be our inside function, and then that's the one that's going to go inside our outside function. Okay, so we can compose functions F composed of G. We could also do G composed of F. We could do F composed of F, or we could do several compositions. It can be more than just two functions. So let me show you what that looks like. If we have G composed of F, notice here F is the closest one to our input. So that's the one that's going to go on the inside. So this would look like G function on the outside, and then our F of X function is getting plugged inside that G function. Okay. Same thing here. We can compose a function with itself. All that means is that we're taking this inner function f and plugging it into that outside function, which also happens to be f. So basically we're plugging our f of x function inside itself everywhere we see an x. Okay. And then the same thing is true if we have more than one. Okay. We always start with our innermost function. That function is going to go inside our next function, and then that function goes inside our outermost function. So here our outermost function is our f function, right? And then our next function in is our g function, and then our innermost here is our h of x. So we would be plugging h of x inside our g function, and then whatever that equals, we would plug it inside our f function. Okay, so let's go ahead and jump into some examples of what this looks like when we actually work it out. Excuse me. So here it says, given that f of x equals 2x minus 5 and g of x equals x squared minus 3x plus 8, we want to find f composed of g of x. So f composed of g of x means that g of x is the inner function, right? And we're plugging that into our f function. So I just want to write out what our f function does. Okay, because remember, when we say we're plugging something into our f function, whatever we plug into that f function, all we're doing is plugging that in everywhere we see an x, right? So our f function says to take what's in our parentheses, we're going to do 2 times that input and minus 5, right? So 2 times our input and minus 5. And what happens to be our input in this function is g of x, right? That's what we're plugging in. So we need to plug in this whole g of x function as our input here. So that's x squared minus 3x plus 8. And now that we've plugged in g inside our f function, now we just simplify. So we're going to go ahead and distribute this 2 to all 3 terms. So that's going to give us a 2x squared, a minus 6x, and a positive 16. And then we also still have this negative 5 out here. So we combine what we can, which in this case is just our constant terms. So we end up with 2x squared minus 6x plus 11, right? So this is our f composed with g function, right? Okay, let's look at a couple more examples, and then I'll have you try one. So on the next page, so we still have the same f function, which is 2x minus 5, the same g function, which is x squared minus 3x plus 8 that we used in the last example. But this time we're finding g composed of f and g composed of itself, g composed of g. Okay, so let's look at g composed of f first. So this means our f is our inner function, right? And that's what we're going to be plugging into g. So this is going to look like g composed of f of x. Okay, so before I worry about what I'm plugging in, I want to worry about what does g actually do to our input. Okay, so if I look at our g function here says we take whatever the input is and we're going to square that input, and then we're going to subtract 3 times that input, and then we're going to add 8 to it. Okay, so I'm going to go ahead and write out what my g function does. This says we're going to take our input and square it. Then we're going to subtract 3 times our input, minus 3 times our input, and then we're going to add 8. Okay, so all I did was write out what this g function does to our input, or in other words, I put parentheses everywhere I see an x. So now I have to plug in what my input in this function actually is. So we are inputting our f of x function in. So f of x function is 2x minus 5. So everywhere that I have an open input, or everywhere I have an x in my g function, I'm plugging in that 2x minus 5. So 2x minus 5 goes in here, 2x minus 5 goes in here. And now we just have to go ahead and simplify this mess. Okay, so I'm going to go ahead and write out what this means. Now, when you square a quantity, that doesn't mean we just square each piece of that quantity. That means we have 2 copies of that quantity, right? This is 2x minus 5 times 2x minus 5, right? And then here, I can go ahead and distribute this 3 to both terms. So that gives me negative 6x plus 15, and then plus that 8 that's out there. Okay. So before I can keep going, I need to go ahead and FOIL this mess out so that I can combine my like terms, right? So 2x times 2x gives me 4x squared. 2x times negative 5 gives me negative 10x. Negative 5 times 2x gives me another negative 10x. And negative 5 times negative 5 gives me a positive 25. Right? And then I'm going to go ahead and write these other 3 terms that were still here. So negative 6x plus 15 plus 8. Right? So now that I have it all written out, now I want to go ahead and combine my like terms. Right? So when I combine like terms, I have, let's see, 4x squared is my only x squared term. So I have 4x squared. When I look at my x terms, I have negative 10x, and negative 6x. So negative 10 and negative 10 is negative 20. Minus 6 leaves me with negative 26x. And then I look at my constant terms, right? I have 25 and 15, which gives me 40, plus 8 gives me a positive 48. So this is my new composed f of g, or sorry, g of f function, right? Okay. All right, let's look at the next one they want us to do. The next one they want us to do is g composed of g of x. So notice here, we're taking that g of x, we're plugging it back into itself. So this one looks like g composed of g of x. So first, before we worry about what the input is, I just want to write out what does the g function do, right? This is the same function we used last time. So notice here, the g function takes our input and squares it. So I'm just going to use parentheses to square it. Then we subtract 3 times our input, and then we add 8, right? So again, not worried about the input. We're just writing what the g function does. It takes our input and squares it. Then we do minus 3 times our input, and then we add 8 to whatever that equals. Okay, now we can worry about what we're actually plugging into it. So what we're actually plugging in here is our g of x function. Our g of x function is now our input, right? So g of x is x squared minus 3x plus 8. So in each of these input parentheses, I'm going to be putting in x squared minus 3x plus 8. X squared minus 3x plus 8. Okay, and then I'm going to work this out the exact same way I did the last one. Okay, a squared quantity means I have that quantity times itself. So here I have x squared minus 3x plus 8 times x squared minus 3x plus 8. And then I'm going to go ahead and distribute this negative 3 into all these terms here. So that's going to give me a negative 3x squared. Negative 3 times negative 3x gives me a positive 9x. And negative 3 times positive 8 gives me a negative 24. Okay. And then we also have this 8 that was sitting out here before. Okay. All right. So let's go ahead and now FOIL out this massive thing. Okay, so we do the same thing we did when we multiplied a binomial times a binomial, except this time we have a trinomial times a trinomial. So I'm going to take x squared and distribute it to everything. Then I'll take negative 3x and distribute it to everything. And then I'll take the positive 8 and distribute it to everything. Okay, all right, so x squared times x squared gives me x to the 4th. X squared times negative 3x is negative 3x cubed. And then x squared times positive 8 is positive 8x squared. Okay, so I'm done with the x squared. Now I'm going to move on to the negative 3x. Negative 3x times x squared is negative 3x cubed. Negative 3x squared times negative 3x, sorry, not x squared, I apologize. Negative 3x times negative 3x is a positive 9x squared. Negative 3x times 8 is a negative 24x. And now I'm done distributing the negative 3x, and I'm going to move on to the positive 8. So positive 8 times x squared is a positive 8x squared. Positive 8 times negative 3x is negative 24x. And positive 8 times positive 8 is a positive 64. Right? Okay, so this is what I got from distributing these two, and now I should still have these other 4 terms, which I'm going to write out to the side here. So I get negative 3x squared plus 9x minus 24 plus 8. Okay, so now that we have everything written out, now we just need to collect and combine like terms. So the highest order term I have here is my x to the 4th. So I'm going to go ahead and just write this as x to the 4th. And then I need to look at my next term. So I use that one. So now I have negative 3x cubed and negative 3x cubed. And those are all the x cubes I have. So that gives me a negative 6x cubed. Okay, and then I want to look at all of my x squared terms. So I have a positive 8x squared, a positive 9x squared, a positive 8x squared, and a negative 3x squared. Okay, all right, so 8 and 9 gives me 17. 17 and 8 gives me 25, and 25 minus 3 gives me 22. So I'm left with 22x squared. And then I need to look at my x terms. Okay, so now I have negative 24x and negative 24x. And then I also have 9x. Is that all my x's? Yes. So negative 24 and 24 gives me a negative 48. Negative 48 plus 9 is going to leave me with negative 39x. And then I just have to combine my constant terms. So constant terms, I have 64 minus 24. So 64 minus 24 is 40, right? Plus this 8 gives me a positive 48. Okay. And now that we've simplified it, this is my new g of g function. Okay. All right, so there are two for y'all to try. Go ahead and take a minute to pause the video and find f composed of g and g composed of x using the f and g function that are given. And when you're ready to go over them, or if you get stuck, unpause the video and we'll go over it. Okay? Okay, so let's go ahead and see how you did. So on the first one, we're plugging in our g function into our f, right? Because g was the inside function, and that's what we're going to plug into the outer function. So before I look at what g looks like, I want to see what f does to my function. So f takes my input, it does 3 times my input and subtracts 1. So notice here in black, I wrote 3 parentheses minus 1. So I know that my f function does 3 times whatever my input is, right? And then subtracts 1. Now I can go ahead and put in what my input is. My input is the g function, and here my g function is x squared plus 4x. Okay, so that's what I'm plugging in. And then all I have to do is distribute the 3 to simplify that first one. All right, let's look at the second one. Second one, we're starting off with the g function, right? Because this is g composed of f of x. So f of x is what's going to go inside that outer g function. So we have g is what we need to know what it does to our input. So whatever I plug into g, if you look over here, it squares the input and then adds 4 times our input. So in parentheses, before I wrote what goes in these parentheses, I put parentheses squared plus 4 times parentheses so that I know this is where my input goes. Okay, and then my input's going to be my f of x function. So my f of x function is 3x minus 1. So that's what I'm plugging into each of those parentheses. Okay, make sure when you square this quantity, you're writing 2 copies of the quantity before you start multiplying it out. Okay, then we distribute our 4 over here. When we collect our like terms, we should end up with 9x squared plus 6x minus 3. Everybody okay so far? Okay, so maybe not too bad to just come up with the composed functions, but now we need to talk about when we come up with these composed functions, how to find the domain of those composed functions. Okay, so we're going to look at that on the next page. The domain of a composed function. Basically, we just need to end up with the values of the variable that we can plug in without getting an issue. So if you remember back to our domain issues, we have to make sure that if we have a rational expression or a fraction, right, the bottom can't be 0. Which if you look at these two that were given, neither of them they're not rational, right? They don't have a denominator that we have to worry about. So that's our first problem. Second problem is we have to worry about if we have an even root radical, like a square root or a 4th root or an 8th root, right? Even root radicals can't have negative numbers under them because that turns into complex numbers, which we don't want to deal with right now, okay? So if we have something like this, we have to make sure whatever's in here stays 0 or positive, right? We can't have a negative in here. So that's the first thing that we want to do is make sure that we know the domain of each function because that will be the starting point when we compose them. Okay, so before we get started, I want to go ahead and just figure out the domain of each of these. So if I look at this f of x function, okay, I see that I have an even root, okay. So notice it says we're going to find the domain of each. Before we can find the domain of each of our compositions, we have to know what our starting domain is. So if I want to find the domain of f of x, okay, I know that whatever's underneath my radical can't be negative. So the way that we write can't be negative with math terms is we say that 2 minus x has to be greater than or equal to 0, right? Because I can't have it be negative. So it could be 0 or it could be anything bigger than 0. And now this is something that I should be able to solve, right? I'm going to go ahead and just move my x to the other side by adding. So I'll have 2 is greater than or equal to a positive x when I move it over, right? And then if I read this, I know we usually write our x first, right? I moved it to that side just to get rid of the negative, but we can rewrite this with the x first. Notice the inequality is pointing at the x, so when you rewrite it, it should still be pointing at the x. So what this says is that x has to be less than or equal to 2. In order for there not to be a negative number under this square root, we can only plug x's into this that are less than or equal to 2. Okay, so I want to go ahead and write that interval notation. That's how we usually write domain. So if it's anything less than or equal to 2, that means it can be anything all the way out to negative infinity, up to and including 2. Okay, so this is the domain of my f function. Then if I look for the domain of my g function, right, domain of g of x, if I look at this one, notice I don't have any denominators to worry about, and I don't have any radicals, right? I don't have any square roots, fourth roots, anything like that to worry about. So when we have no issues, that means that we can plug anything into this function, right? So this would be from negative infinity to infinity. I have no issues with that one. Okay, so we have one function that we can only plug in from negative infinity to 2, and we have one function that we can plug anything into. So we're going to go ahead and keep that in mind as we're coming up with our new composition functions. So the new composition functions they want us to find are f composed with g of x. So notice here we're going to be plugging our g of x function into our f function. So I'm going to go ahead and write, this looks like f composed of g of x. Okay, now whichever function is on the inside, right, that's the function we're starting with, right? So whatever's in here, that's the domain that you're going to be starting with. So since we're starting with g, that means initially we can plug anything we want into our g of x function. So far we have no issues because we're plugging in g. G can use anything, right? But we're plugging that into our f function. So let's ignore this for just a second and write out what our f function does. Our f function takes the square root of 2 minus our input. So square root of 2 minus whatever our input is. Okay? All right. So our input here is our g of x function. So I'm going to go ahead and write in our g function. So we're plugging in x squared plus 4. X squared, oh wait, you know what? I think I was going to change this one. Yep, I was. I'm sorry. So let's make g, instead of x squared plus 4, let's make it x squared minus 2. I apologize. Hopefully I will have changed this on your notes by the time you get here. But if not, if your notes say plus 4, change it into a minus 2. Okay, so x squared minus 2. There we go. Okay. So now that we have plugged our g function into our f function, now we can simplify and think about how that has affected our domain. So the first thing I want to do is distribute this negative to both things that are underneath there. So this is going to give me the square root of 2. When I distribute the negative, I get minus x squared plus 2, right? So now I'm going to combine my like terms, which are my 2's. So I end up with the square root of 4 minus x squared, right? And this is as far as I can go in terms of simplifying, because even though x squared is a perfect square and 4 is a perfect square, I can't take the square root of them individually because they're stuck like glue together with the subtraction sign, right? So this is as far as we can go in terms of coming up with the new function, but I also now have to worry about the domain, because what we're plugging in something that says all x's are okay. We have no issue. We can plug everything in. And if I look at what I ended up with, that's not true, right? I can't plug anything into this because the function that I ended up with has an even root radical. And even root radicals, I have to make sure that whatever's underneath them stays non-negative, meaning 4 minus x squared has to be greater than or equal to 0. Okay, so when I look for the domain here, I know that 4 minus x squared has to be greater than or equal to 0. Now this one's a little bit different than how we solved the f function up here in blue. This one in blue is really easy to solve because I just had an x to the first power, so I could just move it over, right? But here I have an x squared. So an x squared, I can't move it over and take the square root. That does not work with inequalities. That only works with equations. So I'm going to first think about, if I want to make sure this is 0, or anything bigger than 0, I'm going to first figure out, okay, well, what would make it 0? What could I plug in for x and square it so that when I do 4 minus that, I end up with a 0? Okay, so if I think about what would make this, well, in order for me to subtract these and it be 0, x squared would have to equal 4, right? So that when I do 4 minus 4, I get a 0. So what can I square to get 4? Well, I could square a positive 2 or I could square a negative 2, right? So if I use a plus or minus 2, then this thing would equal 0. So I know it's okay for it to equal a positive 2 or a negative 2, right? But what about all the numbers in between those? So let's think about it on a number line. Here's where negative 2 is. Here's where 2 is. So let's think about if we pick a number smaller than negative 2, right? Let's say we pick negative 3, okay? If I pick a negative 3 and I were to plug it in here, negative 3 squared would be 9, right? And 4 minus 9 gives me a negative, which then I would not be able to take the square root of. So over here, I can't use answers that are over here. I can't use numbers that are less than negative 2 because they would cause this to be a negative, right? Let's pick something that's in between negative 2 and 2. Let's pick like 0, okay? If I plug 0 in up here, 0 squared is just 0, and 4 minus 0 is 4. And I can take the square root of 4, right? So over here, I can use anything in this interval. That interval is okay. And then let's look at something that's bigger than 2. So let's pick, I don't know, we could pick positive 3. If I pick positive 3 and plug it in here, I'm going to have the same problem I had with negative 3, right? Because positive 3 squared gives me a 9, and 4 minus 9 gives me a negative, and I can't take the square root of a negative number. So this interval doesn't work. So notice the only values that I'm able to use here are anything that falls between negative 2 and 2. And because we want it to be greater than or equal to 0, it could be 2. So I can also include those points. So here the domain that I get, my domain would be negative 2 to 2. Okay. So on your homework, these problems will be in 2 parts. They'll have you find the composed function, and then they'll also ask you to find the domain of that composed function. Okay. And not all of them will be this intricate, but I just want to make sure you've seen one like this, where if we have a squared, right, we have to think about, well, what will make this statement 0? And then from there, we can test outside of those 0 values. Okay. All right. Let's look at going the other direction. So that was finding f composed of g. Now we want to find g composed of f. So this time, our f function is what's on the inside, and we're plugging it into our outer function, which is g. So we're going to do g composed of f of x. Now with f of x being the inside function, that means we're starting with f of x's domain. So if we look back up here, the domain of f of x was negative infinity up to 2, right? So we can plug in anything into this f function that's from negative infinity up to and including 2. Okay, so we're starting out with a restriction. If we encounter more restrictions, then we will adjust it accordingly. Okay, if we don't encounter more restrictions, then this will just be the domain of this new composed function. Okay, all right, so before we worry about what we're plugging in, let's think about what the g function does. If I look up here, the g function takes my input and squares it and then subtracts 2. So we're going to take our input and square it and then subtract 2. Okay, and then our input here is our f function. So if I look at what my f function is the square root of 2 minus x. Okay, so now we just need to simplify. Notice here I have a square root being squared. When we square a square root, those cancel out. right? So this just becomes 2 minus x from what was in here, right? Because the square and the square root canceled, and then minus 2 that was left out here. Okay, and then notice if I combine like terms, I have a 2 and a minus 2. Those cancel out, and I'm just I'm just left with negative x. So negative x is my new composed function. Now, looking at this, does this have any stipulations? Do I have any denominators? Nope, don't got to worry about that. Do I have any even root radicals? Nope, I don't have any even root radicals. So notice this little piece has no new restrictions. So if there's no new restrictions, then the domain of this is going to be whatever that original inside function domain was that we started with. So here, my domain is going to be negative infinity to 2. Okay. So I just want to kind of reiterate that. Even though this didn't have restrictions, our domain still has restrictions because we came up with this function starting with our f of x. And since f of x had restrictions, this is going to be my domain unless I encounter further restrictions as I work out the problem. Okay? All right, let me do one more example of this type where we have to not only find the function, but we have to find the domain, and then I'll give y'all some to try. Okay? All right, so on this one, let me make sure I didn't change any of the problems. No, we're good. Okay. Okay. So on this one, it says given f of x is 6 over x and g of x is 1 over 2x plus 1, find f composed with g and g composed with f and the domain of each. Now, if we're finding the domain of each, it's very helpful to start off knowing what the domain of each is. Okay, so when I look for the domain of f of x, okay, domain of f of x, notice I don't have any even root radicals, right? I don't have any square roots, fourth roots, anything like that to worry about, but I do have a denominator, right? And denominators cannot equal 0. So here we know that x cannot equal 0, right? And that's all that I have in the denominator. There's nothing further to solve. It's just x can't be 0. So if x can't be 0, that means x could be anything else. We can plug in anything into this function other than 0. So that means our domain would be from negative infinity to 0 or 0 to infinity, right? We're just taking out 0. Then I want to go ahead and find the domain of my g of x function. So my domain of g of x is very similar, right? We don't have even root radicals, but we do have a denominator here. And whatever our denominator is can't be 0. So this means that 2x plus 1 can't be 0. Oops, 0, right? So I'm going to go ahead and solve this because unlike the last one it was just x can't be 0 because that's all that was in the denominator. Here we have more than just x in the denominator, so we actually have to solve for what x values it can't be. So if I move my 1 to the other side by subtracting, that means 2x can't equal negative 1, right? And then I divide off my 2. So here x cannot equal negative 1/2. So again, it could be anything from negative infinity to positive infinity, but we have to take out take out negative 1/2. So this would be negative infinity to negative 1/2 or negative 1/2 to positive infinity. Okay. All right, so now we know our two starting domains. They both have restrictions. Now, knowing that they both have restrictions means that any type of composition function we do is going to end up with restrictions because we're starting with restrictions, okay? All right, so let's work out the first one. The first one they want me to find, or they want us to find them together, is f composed of g of x, okay? So g of x is our inner function that we're going to be plugging into our outer function f. So this looks like f composed of g of x. So if g is on the inside, that's the function we're starting with, okay? So I'm going to go ahead and instead of writing it out like this, I'm going to go ahead and just use the shorthand notion. that x cannot equal negative 1/2, just to kind of save some space. Okay, if this ends up being my only restriction, then I'll write my domain like this in interval notation. But just for the sake of saving some time and some space, I'm going to write it like that. Okay, all right, so I'm going to ignore G for just a hot second and write what F does to our input. F takes 6 and divides it by our input. So 6 over our input. Okay. And notice here, our input is the G function. So if I look at the G function that I'm plugging in is 1 over 2x plus 1. Okay? 2 over 2x plus 1. I'm sorry, 1 over 2x plus 1. Okay? All right, so now we just need to simplify this. Now, this is a complex fraction, and we don't ever want to write our answers with complex fractions. So a complex fraction means I have a fraction within a fraction. And so we can think about this as a division, right? Fractions just represent division. So what this really says that we're doing is we're taking 6 and we're dividing it by 1 over 2x plus 1, right? And remember, whenever we divide fractions, or you can write this as 6 over 1, so that they're both written as fractions, right? When we divide fractions, that's where we use our little space gun, right? We pinch and pew, pew, it turns into a multiplication and flips this one, or we multiply by the reciprocal, or some of you may have learned keep, change, flip, or something of that sort, right? So we multiply and flip the second one. So this gives me a 6. This now becomes a multiplication of 2x plus 1 over 1, right? And again, we can still write this as 6 over 1. So if I multiply straight across, I'm just going to end up with 6 times 2x plus 1, and that's all over 1. So if it's all over 1, we don't really need to write the 1, okay? But I am going to go ahead and just distribute the top. So this gives me 12x plus 6. So this is my new composed function, and now I just have to state the domain of that new composed function. So notice we started off with the restriction that it cannot equal negative 1/2, and now I look at my finished product to just make sure I don't have any further restrictions. Do I have denominators? No. Do I have even root radicals? No. So I didn't end up with any more issues than I already had initially, which means that my domain of this function will be negative infinity to negative 1/2 and negative 1/2 to infinity. Is everybody kind of okay with that? Okay. If we would have had more restrictions, we would have taken this domain and, taken out more things or whatever needed to be done. But in this case, we didn't end up with more issues, so we just stick with the original restriction we had. Okay. All right, let's look at our next one, which is G composed of f of x. So f of x is our inner function, which we are going to be plugging into our outer function g. So this one looks like G composed of f of x, with f of x on the inside. So if f of x is our innermost function, that means we're going to be starting with its domain restriction. So the only issue we had with f of x is that x can't be 0. Okay? So as long as we don't end up with any other issue, then our domain will be everything but 0. If we end up with further issues, then we'll have to modify it a little bit. Okay? All right. So let's ignore what we're plugging in for a minute and figure out what G does to our function. G function takes 1 and divides it by 2 times our input plus 1. So 2 times our input plus 1. Okay? And now we just need to put in what our input is. Our input here is our f of x function. And f of x is 6 over x. So this is 6 over x. Okay? So we're going to go ahead and now simplify this as best we can. Excuse me. So if we simplify this, I get 1 over, when I multiply here, we can think about this as 2 over 1. So multiply straight across, we get 12 over x plus 1. And then do y'all remember when we did that section, I think it was J27 or J26, it was one of the review sections where we talked about how to get rid of complex fractions by multiplying by the least common denominator as a form of 1. right? So whatever will get rid of all of the denominators, I can multiply as a form of 1. So here, if I look for my least common denominator, the only denominator that I need to get rid of, if I look at all three of these terms, is that x. So really, it's like I'm multiplying by x over x, because that, when I distribute it to this term, will cancel out the x, right? And that will leave me with something that's not a complex fraction. And I'm not changing the value because I'm just multiplying by the least common denominator over itself, which is a form of 1. Right? So I'm going to go ahead and just rewrite this with x written next to everything so that you can see how it's going to cancel out. So I'm going to have 1 times x on top. On bottom, I have 12 over x times x plus 1 times x. Okay? So when we say we're multiplying by x over x, we're really multiplying everything on top and bottom by x, so that this one denominator that I do have will cancel out. And what I'm left with is an x on top, and on bottom I have 12 plus x. Okay? And notice I can't reduce any further here. I can't reduce these x's as much as I'd like to, because this one's stuck like glue to that 12 with that plus sign. So this is a quantity, and we can't cancel pieces of quantities, right? So this is my g of x function, and now we have to talk about the domain. Okay, so originally we know that x cannot be 0, right? And now we have to think about, okay, do we have further restrictions? And here we do, right? We don't have any square roots or anything, but we do have a denominator, right? And we know that here our denominator, 12 plus x, cannot equal 0, right? So if we solve this by moving that 12 to the other side, that tells me that x cannot equal negative 12. Okay, so now we have two stipulations. We have the original stipulation that x can't be 0, and now we also have the added stipulation that x can't be negative 12. So when we write out our domain, we have to make sure it accommodates both of these. So it can be anything except 0 and negative 12. So I'm going to start at negative infinity. So it can be anything in the negative direction up to our first issue. So our first issue here would be negative 12. And then it could be anything from negative 12 on over to our next issue, which is that it can't be 0. So I got to take 0 out. But then it can be anything bigger than 0. Okay, so this is our domain. Okay, is everybody kind of okay? I know it seems like a lot of work for one problem. The idea is we want to make sure we know the domain of each function so that when we compose, we start with the domain of our innermost function. Okay, once we have it worked out, if there's no new restrictions, then our domain for this new function is just whatever the domain was of that original innermost function. Okay? If, when we work it all out like this one, we got something that has additional restrictions, like here x can't be negative 12, then our domain is the combination of our new restriction and our original restriction. Okay? So we take the most restrictive combination of the two. Okay, so there is one for y'all to try at the bottom of the page. Go ahead and pause the video, and then when you're ready to be checked, or if you get stuck, unpause it and we'll go over it. Okay, let's see how you did. So on the first one, they're wanting us to find f composed of g of x. So g of x goes on the inside and f is on the outside. Now, in order to be able to find the domain of this composed function, I need to know the domain of g. So if I look at g, notice this is just a regular polynomial function. There's no denominators, there's no square roots. So that means there's no domain restrictions. So I'm starting off with no domain restrictions, and I'm plugging that g function into my f function. My f function says to take the square root of my input. So I'm taking the square root of my input, which is my g function. G function is 2x plus 1. Okay, now there's nothing I can simplify here. This is not a squared quantity, so it doesn't simplify. So we're just going to leave it as a square root of 2x plus 1. And then we would say, okay, our domain is still all real numbers, but we ran into a domain restriction here, right? Because we have a square root. And we know that square roots cannot have negatives under them. It needs to stay non-negative. Or in other words, whatever's underneath here, 2x plus 1, has to be greater than or equal to 0. So we're just going to go ahead and solve this one. It's just an x to the first power, so I can just solve it for x. So I move my 1 over by subtracting, and then I divide my 2 off, which says that x has to be specifically greater than or equal to negative 1/2. So I went from no restriction to restriction. So the most restrictive combination of these two is what my domain is. So that's going to be this one. So my domain is going to be from negative 1/2 to positive infinity. Okay. All right, let's look at the second one. The second one, we're supposed to find g composed of f of x. So now f of x is our inner function being plugged into g of x, which is our outer function. Remember, we start with the domain of our inner function, so we need to know what the domain of f is. So if I look at this f function, notice I don't have any denominators, but I do have a square root. And we know that whatever's under a square root has to stay non-negative. Or in other words, that x has to be greater than or equal to 0. Okay, so it can be 0 or it can be anything bigger than 0. So that's the domain that we're starting with. Okay. All right, so we're plugging our f of x function into our g function. Our g function says to do 2 times our input and add 1. So I have 2 times my parentheses and add 1. And what we're plugging in is our f function, which is just the square root of x. So when I multiply 2 times the square root of x, 2 is on the outside, x is under the radical, so I can't multiply them, but I can write them side by side. 2 square root of x plus 1. And even though there's no simplifying to be done, this is my final answer, I do need to make sure I find the domain of this function. So this function does have restrictions, right? It has the square root of x. But notice the square root of x was also the original restriction that we had. And we've already accommodated for that with this domain. As long as we pick an x that's 0 or bigger, we have no issues. So even though there is a restriction here, that's not a new restriction. It's one we've already accommodated. So we just keep that same domain, which is 0 to infinity. Okay? All right, so we've looked at how to find composition functions. We looked at how to find composition functions and their domains. The last thing we need to look at is how to evaluate composition functions. And remember, composition functions, when we evaluate, or not even just when we evaluate in general, it just means we're plugging something into it. Okay, so we're going to have to be a little bit conscious of our domain to see, first of all, is it something we can even plug into it? And then there's a couple of different ways to do it. So I'm going to go ahead and show you that here on the next page. So this one says, excuse me, given that f of x is equal to 2x minus 5 and g of x is x squared minus 3x plus 8, we want to find these three values, right? We want to find f composed of g of negative 1. We want to find g composed of g of negative 1. And we want to find f composed of f, oh, there's 4, of 3/2, and then g composed of f of 1. Holy moly, we got lots of examples, right? All right, so let's go ahead and just start with the first one and write down what this means. Okay, we have g closest to the input, so we're going to do g of 1, and that will go into our outer function f. So this looks like f composed of g evaluated at 1. So we write it the same way we always have. The only difference is we have an actual value to plug in, right? We have an actual value to plug in versus just an x. So there's two ways to do this. We could figure out what is the f composed with g function. We could find that new function, and then once we have that new function, we could plug negative 1 in everywhere we see an x. Or we can do this one piece at a time. Since it's already written like this, g of 1, if this was not here, if this outer function wasn't here, we know how to find that. That just means we're plugging negative 1 into our g function, right? So let's go ahead and do that. Let's just plug negative 1 into our g function and figure out what this equals. Okay, so our g function says whatever we plug in for x, we're going to square it and then subtract 3 times our input, and then add 8. Okay, so I'm just going to go down here and find g evaluated at -1. So I'm plugging a -1 in everywhere I see an x. So that's going to give me a -1 squared minus 3 times -1 plus 8. And then I'm just going to simplify this. Right? -1 squared is a +1. -3 times -1 is a +3. And then I have +8. So 1 plus 3 is 4, plus 8 gives me 12. So what we just found that g of -1 is the same thing as 12. So I'm just going to rewrite what it is I'm trying to figure out here. We're trying to find f of g of -1, which we just determined is 12. Okay? And now that we've simplified that, now this last piece should be a lot easier, right? Now we're just finding f of 12. So 12 is what we're plugging into our f function. Our f function says whatever's in the parentheses, we're going to do 2 times that value and subtract 5, right? So we're going to do 2 times the value in our parentheses, which is 12, and subtract 5. Okay? And then we just need to finish, and we just need to simplify this, right? 2 times 12 is 24, minus 5 gives me 19. Okay, so that means f composed of g evaluated at -1 equals 19. Okay, you can also think of this with the arrows that I showed you at the beginning. It's like you're taking this -1, plugging it into g, and then whatever that equals, you're plugging into f. Okay, let's look at another one. Let's look at g composed of g evaluated at 1. G composed of g evaluated at 1, right? So this means we're plugging 1 into our g function, and whatever that equals, then we're going to plug it back into our g function. Okay? So when we get started, we're going to start by figuring out what does g of +1 equal. Okay? So we're going to plug 1 into our g function. Our g function says to square our input, then subtract 3 times our input, and add 8. So we're going to go ahead and evaluate, which gives me 1 minus 3 plus 8. 1 minus 3 is -2, plus 8 gives me 6. Okay, so now we know that g of 1 equals 6. We can go ahead and rewrite this with a 6 in here instead of a g of 1, because we just figured out what that equals, right? And now we can go ahead and simplify this, right? So now we're plugging 6 into our g function. So again, we're using this function, which says to take our input, square it, and subtract 3 times our input plus 8, right? And our input here is the -6. So I'm just putting -6 in there and then simplifying. So 6 squared is 36 minus 3 times 18, or sorry, 3 times 6, which is -18, plus 8, right? So 36 minus 18 is 18, right? Plus 8 gives me 26. So this is what g composed of g evaluated at 1 equals. Okay, let me do 2 more, and then I'll let y'all try some. So let's look at our next one, which is f composed of f of -3/2. So we're going to take that -3/2, plug it into f. Whatever that equals, then we'll plug that back into f. So in other words, we're doing f evaluated at f of -3/2. Okay, so before we get started, we want to start with our innermost evaluation here. So we need to figure out what f of -3/2 looks like. So my f function says to do 2 times my input and subtract 5. So I'm doing 2 times my input of -3/2 and subtract 5. So when I do that, notice here, if I multiply straight across, I would get negative 6 over 2, which then reduces down to negative 3. Or you can think about just canceling these 2's here, right? And I end up with negative 3 minus 5, which gives me negative 8. Okay? So we figured out what this innermost evaluation equals. It equals 8. So I'm going to go ahead, or sorry, negative 8. So I'm going to go ahead and replace that with negative 8. And now negative 8 is what we're going to re-plug in to our f function. Okay? And again, our f function says to do 2 times our input and subtract 5. And here my input is negative 8. So when I simplify this, I end up with negative 16 minus 5. And negative 16 minus 5 gives me negative 21. And that is what f composed of f evaluated at negative 3/2 looks like. Okay. I want to do one more, and then y'all can practice it. So my last one says we want to do g composed of f evaluated at 0. So we're plugging 0 into f. Whatever that equals, we're plugging that into g. Now, I know some of these you're going to be able to do in your head, but I really encourage you as you're doing these homeworks to write it out, because on your exams, on like the final, things like that, you know, I'm going to be looking for these steps. I'm not going to necessarily count it wrong if you don't show every little step, but if you get the wrong answer, if I can see where maybe you just made like an error right here, I can still give you a decent amount of partial credit, versus if you just give me an answer and it happens to be wrong, I can't give you any credit. Does that make sense? Okay. All right, so let's try our last one. This is g composed of f evaluated at 0. So the first thing I want to do is this innermost computation, which is f evaluated at 0. My f function says to do 2 times my input and subtract 5. So I'm going to do 2 times 0 and subtract 5, which is just 0 minus 5, which then is just negative 5, right? So I'm going to go ahead and replace this f of 0 with what I found it to equal, right, which is negative 5. And then negative 5 is now what we're going to plug into our g function. So I'm going to scroll this down for just a second. So our g function says to do our input squared minus 3 times our input plus 8, right? And then our input in this case is negative 5. I'm going to go ahead and simplify that. Excuse me. So this gives me what? 25 plus 15 plus 8. And then we just need to simplify. So 25 and 15 gives me 40, plus 8 is going to give me 48 for this composition. Okay? All right, so there are 4 composition functions for you to evaluate on the next page. Whenever you are ready, or if you get stuck, go ahead and unpause the video. I want you to pause it while you work it out, okay? Don't just let it play and copy down everything I do. I want you to pause it, try to work it for yourself, okay? And then when you're ready to check yourself, or if you get stuck, go ahead and play it, and we'll see how you did. Okay, let's see how you did. Notice here we have 2 polynomial functions, so there's no domain restrictions of either one. I can plug anything I want in here. I can plug anything I want in here. I could have written negative infinity to infinity, but I just used the double bar, capital R, to mean all real numbers. So we have no restrictions. So we should be able to fill out and evaluate all of these compositions. Okay, so our first one is f composed of g of negative 1. So that means I'm putting negative 1 into my g function. Whatever that equals, I'm plugging into my f function. So g of negative 1 is what I need to evaluate first. When I plug that into my g function, I should get 5. Okay, so I'm just going to replace my g of negative 1 with 5. And now 5 is what I plug into f. F says to do my input and subtract 3. So input of 5 minus 3 should give me an answer of 2. Okay, everybody okay on the first one? On the second one, we're doing g composed of g evaluated at negative 2. So negative 2 goes into g. Whatever that equals, we're plugging it back into g. So when I plug negative 2 into g, we should get 17. And that is what we're now going to plug back into g. Okay, G says to do 4 times my input squared plus 1. So when I square 17, it comes out to a huge 289 times 4 is 1,500 or 1,156 plus 1. So some of these can give us ugly answers. Don't stress out. If you're doing it correctly, don't worry about ugly answers. Okay, they happen. All right, and then let's look at our last two. Our last two is F composed with itself. When we put 1/2 into F the first time, we end up with -5/2. Now here, 1/2 minus 3, this is something you should be able to do in your calculator. If you don't have your calculator handy, you'll have to do a common denominator like I did here. Okay, either way, you should get -5/2. Don't enter that as a decimal, leave it as a fraction. When we plug in -5/2 into F again, then again, we'll have something we need to do on our calculator or get a common denominator for. Either way, we should end up with -11/2. Okay, and then our last one, we're doing G composed of F at 0. So we're going to put 0 into our F function, and whatever that equals, then we're going to put that into our G function. F evaluated at 0 gives us -3. Oops, I have a typo here. I don't think it'll affect my answer, but 0 minus 3 is a -3. So -3 is what I'm plugging back into G. And G does 4 times my input squared plus 1. And yes, it did not make a difference because when I square -3, it does give me 9. So we should end up with 37. Okay. All right. That is the end of section 2.3. So you should now be able to complete the My Math Lab assignment for this one. If you have any questions or need help, just let me know.